So in the last class, okay, so before we start, if you have any doubt, because in the last class we have introduced the metamaterial and we have given a very basic perspective that what are the different types of metamaterial. We have also talked little bit about the auxetic metamaterial, then negative mass, negative stiffness, different types of thing, and why these materials are called as metamaterial. Okay, so with this background, today we will going into the fundamental of the wave propagation. So now let's see, because once we were discussing in the last class, the first and foremost point was that this course has three prime important point, that is waves, periodic structure, and then metamaterial. So now we have already discussed about the metamaterial. Now we will going today waves and periodic structures, and we will see how they are actually. So let's today start discussing on the wave propagation first. So if we see wave propagation and periodic structure, so if we see, and also in the last class we have seen that metamaterial are one type of periodic structure as well. So they are actually the internal structures are repeating, like for example we have some sort of like honeycomb type shape was there, like this type of honeycomb shape was there, and that shape, if you see, that is repeating. एक मिनट काट सकते हैं. This structure is repeating. So in this thing, and now we can also think like we may have some beam with some type of resonators, means the spring mass attached at the periodic distance, attached after certain distance. So periodically some resonators are attached. Maybe this is like a beam with some supports which are also periodically placed. So these different type of the structures we can think. Now the prime point is that how wave will propagate through this type of structure, and what can we get from that, and what is the speciality that wave within the periodic structure. Okay, so now if we try to see that thing, so the first point, if we think what is wave, so wave is primarily, we can think, some sort of excitation which is placed over the, means which has both the component in the space and also as well as in the time. So once a wave is propagating inside a medium, each and every location or each and every particle within the medium experiences some sort of vibrations, and that vibrations is propagating with some sort of harmony, and we can able to get that complete wave field. For example, if you think like just like a string, so then each and every point of the string will oscillate, but they are not oscillating in a random pattern. Like one point maybe is at this location, like maybe this is at this location, then this one is here, this one is here, then next one is here, next one is here, and then again they are changing. So we can able to see, once wave is propagating, then we can see that wave can be, we have this two component, means in that coordinate space we can write it into the two ways, like one is dependent on time and another is dependent on the space. So primarily we can write it y equal to e to the power xt a into e to the power of minus I omega t into e to the power of minus I k into x. So that is the prime way to write it, or we sometimes write it also in that very combined form, I omega t minus kx or plus kx, whatever. That way also we often write the wave propagation equation. Okay, so if you see, what does that mean to us? That if we are taking at a particular location, so let's say we are telling at let's say a distance, we are looking at a particular point, then what will happen? That point, how it is vibrating? That point is vibrating. So this is the constant value, e to the power of minus I k a into e to the power of I omega t. So this is again a sinusoidal type of vibration. So this is a sinusoidal vibration, and this thing is acting like an amplitude. So we can able to see some oscillation, and that oscillations is this. Okay. Then we can also able to think after certain distance, maybe let's say b. So we can write it a plus b comma t, that is also e to the power of I minus I k a plus b into e to the power of minus I omega t. So that way we can also again write what is the vibration of the other point. So this, so we can see that this portion is now time dependent part. So that shows how the particle is oscillating over the time, and also we can able to see if we are taking a, so this thing is something like if we are placing a accelerometer or some displacement sensor at a particular location, what type of response we can able to plot into that. Okay, so like we placed the accelerometer, we can able to see a sinusoidal type or e to the power of minus I omega t type of response we can able to get there. Okay, any doubt up to that? Anybody? Okay, now if you think, if we are putting something like, now suppose let's say we take a camera instead of putting accelerometer. Let's think we take a camera and we take a snap of that complete field. What can we able to see? So in that case, once we are taking a snap, maybe that time is t equal to t0. Okay, so how that complete field will look like? So then we can write it, the field equation is x comma t0, and that will be e to the power of minus I omega t0 into e to the power of minus I kx. So here we can see this is my amplitude type term, and this become my oscillation in the space. So you can see there are the two things. One, how it is oscillating with time, and how it is varying with space. Both the thing we can able to see in a very nice manner. All of you agree with me? Any doubt? Now, if you think, there is another important point we need to also consider. That is, what is the meaning of that omega and what is the meaning of the k? So meaning of the omega is, that is temporal frequency. That means how quickly or how quickly like these full frames are actually getting changed. And kx is in 1 meter how many waves are packed. Okay, so both the things are like some type of reciprocal. So omega is reciprocal of the time and k is reciprocal of the space. Okay, therefore the reciprocal of the time is known as temporal frequency. Temporal frequency. And what is reciprocal of the space? That is known as spatial frequency or wave number. Like number of waves present in unit length. Agreed? Make sense? Good. So that two way we can able to see that full matter, that how they are actually placing. Any question up to that? No question. It's quite standard, quite straightforward thing. Now the most important thing is coming. Now, up to this stage is all okay. Now, if you think what people were thinking that now there is a important thing happen once we are talking about the periodic structure. Now you thought that your structure is oscillating as like a periodic manner, or as like a some wave is propagating inside that structure. Okay, very good. Now if you think that wave is propagating inside the structure, then what happens? After certain distance, let's say you have a periodicity which is a distance, like if you take this case that has a periodicity up to a distance. So suppose if I try to calculate what is the response of this particular point, means if I put a accelerometer at that location, what will be my responses? My response will be, maybe I am just writing it node 1, node 2, node 3. So y1, so that will be varying with time or space. Anyone? Time, exactly. Because space already fixed, I'm varying with time. So that will be a into e to the power of minus I omega t with e to the power of minus I k. Let's say that distance is x. What will be y2t? X plus a. Agreed? What can I write? Can I write it? Because that full term is nothing but this. Can I write that? Agreed, all of you? Great. What about y3? You can think that will be also very similar manner. So I can write it e to the power of. Agreed? So now, very important point. If you see, we can write the the displacement or the response within a periodic structure after certain distance. We can see that they are repeating, and repeating means they are not exactly repeating, they are actually following some correlation. They are correlated, they are not repeating. That means repeating means they are becoming exactly same. It is not repeating, but they are correlated. And most importantly, so if I think that y3 is equal to e to the power of minus I k into 2a into y1, y2 equal to e to the power of minus I k into a into y1. So now you see that whatever the distance is from y1, whatever is the distance, that distance is actually coming here. Other things are remaining constant. Agreed? So what is this? So that distance into the wave number is giving me a correlation. I can tell that y2 is equal to the power of minus I k into 2a times, or I into k into that distance times y1. Okay. So we are getting a relationship between the 2 points which are periodically placed, and that correlation importantly have. So now if you think, just a minute, like let's think, if you are, so here in that wave equation there are 2 prime parameters, 3 parameter maybe: amplitude of the wave, omega which is temporal frequency, and k which is spatial frequency by wave number. So we see that now once we are try to finding out that what is the correlation between the 2 points periodically placed, we can see that that is dependent on the wave number alone. Omega is not present in that. Does that make some sense to you? Does that make sense? Good. So this thing we found, and this thing is primarily broadly written as like a Bloch theorem. You maybe, means if you are working in the metamaterial, you maybe heard the term band gap and Bloch-Floquet theorem, which are very much used to resolve that periodicity of the structure. And this is, you can say, like a very simplified way of telling what is the Bloch theorem. In reality, that Bloch theorem was actually came from the electron, like how the electrons are going, moving and all those things. But if you are putting that full thing from the very simplified concept of the wave propagation theory, you can able to derive it like this. Okay. And more importantly, this y can be any quantity, any wave propagation quantity. They can be displacement, they can be bending moment, they can be shear force, whatever. They can be velocity, everything can be possible. Whatever is like a vector quantity, you can able to put it there. Agreed? Any question up to that? Please. Superposition. Same. No. Understood the objective. We are talking that, like, we first assume in that medium we are having a wave. Agreed? And then our target is to find it out. We try to calculating that, okay, what is that one point, what's the another point, what's another point. And these points are placed after a certain distance. Okay? And we try to find it out, is there any correlation between the amplitude of those points. Okay? So that was exactly what we are trying. Okay, so there is no concept of superposition actually comes into it, because we are not trying to finding out like the overall response and all those things. We just try to see that wave is going and whatever is the correlation between these points. Agreed? Any doubt? Okay. Nice. So if you are agreed, good. Now let's try to do a simple system. Now let's assume that we are trying to see the wave propagation through a system where masses m are placed after a distance periodically, and they are connected with each other with a spring stiffness k. Okay, so just think like we are having mass connected by spring k, and we excited, or we are try to see that how the wave is propagating inside that. So that's our objective of try to doing, like we try to find it out how it is actually happening. Let's see. So if this is the scenario, so what can we do? So we have already seen what. So just name it like 1, 2, 3, 4, 5, 6. I just name, and that is going. Here it is also going in the negative side. Okay. My target is to first find it out the displacements between these 2 points. So let's say if I just think like y2, that will be equal to y1 into e to the power of minus I k into a. Very simple. What will be my y3 to k into a? What will be my y0? Anyone? The thing like here we have a y0. What will be y0? Nah, plus. Plus. Exactly. So that way we can able to get that. Agreed? Agreed? Good. So we can get these things like this way. Now, if you think once we are having these like y1, y2, y3, we got all those values. So this way we can able to place that full thing and we can see how the correlations are actually happening. Now think that if we are try to make a equilibrium equation for let's say 0.1, what can we get? So now you think 0.1, that is displaced by y1. This one is displaced by y0. This one is displaced by y2. Agreed? You have a springs in between k, m. Okay. So what will be the force acting on this point and this point? Okay. So what are the forces? So this point will have the inertia force of m into y1 double dot. Agreed? Agreed? How much will be that force? K into y2 minus y1. And what will be this force? This force will be k into y0 minus y1. Agreed? All of you? Any discrepancy? Please feel free. Okay. So if you try to balance it, okay, I just take it all in one side. And now what I am doing, agreed, agreed, all of you. Okay. Now if you are agreed, now think, what is this term? 2 minus e to the power of I k a minus e to the power of minus I k a. How can we write it? Yeah, so it can be written as like, if you remember, what is e to the power of I k x? Cos x plus I sin x. So can I write? And what will be e to the power of minus I k x? Make sense? Agreed? So what will be this? Agreed? So can I write? This portion, what I did, I assume the steady state solution and the harmonic solution. Okay, I can also write it na, that y equal to e to the power like a into e to the power of minus I omega t into e to the power of minus I k x. So what will be the y dot? Sorry, y double dot. That will be the derivative with respect to this term. So I will get it minus omega square a into e to the power of minus I omega t into e to the power of minus I k x. So it will be nothing but minus omega square by y. Okay, got that? Can I write this term, this equation? If I can able to write this equation, now there is a very interesting matter from here. Now think, it is like omega square m plus 2k into 1 minus cos 2ka. This is kappa actually, sorry. Yes, these two things we need to understood. This is kappa wave number, and this is k, stiffness, spring stiffness, into y1, that is equal to 0. So what can be 0? y1 or this term? Which one is 0? Obviously this term is equal to 0, because if y1 becomes 0, then everything will be non-trivial. It's a trivial solution, sorry. So for the non-trivial solution, this must have this thing equal to 0. And if you see very carefully, what can we get it from here? That tells me a very interesting thing. So I'm just rewriting the equation. Minus omega square plus 2k into 1 minus cos kappa into a, that is equal to 0. Now let's see, what are the terms do we have here? We have mass. So you think this is representing this type of structure. So this is representing this type of structure. Okay. So now you will see these are my mass m and these are stiffness k and these are distance a. So this is my mass, this is my stiffness and this is the distance. Okay, agreed. So what are the two things left? That is omega and kappa. So what is omega and what is kappa? That is the temporal frequency and spatial frequency. So it is telling that within some medium, you like wave cannot be just exist. It can only exist when there is a correlation between the wave number and the frequency. Agreed? Because we have a single equation and two terms are there. So that is automatically telling that they have a correlation and they cannot be just some random values. For a particular medium, these relationships should be satisfied for having any wave inside it. Agreed? Agreed? Did you get that idea? So we cannot have any random wave, random frequency, random wave number cannot exist. There should be always a correlation between these two. Agreed? So if you think here, but I have to rewrite that equation a little bit further because we don't know which one we know and which one we don't know. We get an equation or we get an expression that is omega square into m plus 2k into 1 minus cos kappa a equal to 0. Okay. Here we have seen for a particular medium, we know what is the mass, what is the stiffness and how much distance they are placed. That three things we know. But what we don't know, what is omega and what is kappa. Okay. So what is known for the real life? Anybody have any idea? Suppose if we are solving a particular problem, what will be known to us? There are three things is known to us, agreed. Among omega and kappa, what can be known to us? So suppose if we take some structure or some system or something, like let's say I am speaking, it giving some sort of excitation, some wave is going, we can able to still solve that with using that. If we think that we have the air particles after certain distance, they are connected, we can able to solve this similar way. I am speaking, it giving some amplitude, that is basically my loudness of the voice, that is amplitude. Speaking has some sort of frequency. So now if you think what is coming there, so once I am talking, some particular frequencies are actually coming into there. So those frequencies can be known. Then what we can able to calculate? So from here we can see that if we know omega, we can find out k, and on the vice versa, if we know k, we can find out omega. So for the first case, what we just explained, like suppose if I am talking, some machine is revolving, suppose metro is moving, all those cases primarily we have some omega. Or we can think it very good example, if you are going to gym, then there maybe you see that some gym ropes are there. people are taking it and do this type of way and try to generate some wave. Okay, so in that case, once we are doing this, what are we giving? Anybody? What are we giving to the structure? Frequency or wave number? Frequency. So, exactly. So we are giving the frequency to the system. So in normal cases, if we quickly see, mostly found several examples where we are giving the frequency to the system. Okay. So once I say in most of the cases we can found we are giving the frequencies, that means we are primarily solving this thing. So is there any possibility that most of the cases we are doing that? Is there some of the cases where we are giving the kappa, wave number? How can you realize a wave number? Or inputting a wave number, what does that mean to you? Whether did you all of you get that excitation of the frequency? Did you understood that point? The third, like how we can able to excite or give the frequency to the system? All of you get that? Is that clear? Like we are exciting and we can give that frequency to the structure. Make sense? Okay, so now first let's assume we are giving the frequency and let's see how the wave number we can calculate, and then we will try to think what is the meaning of giving the wave number. Okay, let's first try to understand little bit. Okay, so let's first do it like we are giving the frequency and we try to calculate what is the wave number. Okay, so if I go ahead with that, how should we solve it? 2k into 1 minus cos ka, kappa a equal to omega square m. So 1 minus cos kappa a, that will be equal to omega square m by 2k. From there, cos kappa a will be equal to 1 minus omega square m divided by 2k. Okay, so what will be kappa a? That will be equal to cos inverse of 1 minus omega square m by 2k. Okay, can we calculate it? Let's see what are known to us. M, do we know? Yes, this is the mass of the system. K, do you know? This is the stiffness of the system. We know. We know A also. We can write it also 1 by A. We don't need it here. Okay, so A is known to us. Omega we are giving. So like we are giving a particular frequency. So omega is also known to me. So that full right hand side is known to me. Can I calculate what is kappa? Okay, can I calculate it? Yes, perfect. So I can calculate the kappa. I can get the value of kappa. Now here, can you tell me what could be the values of kappa, or how does the value of kappa can be? Is it a positive, negative, real, imaginary, or does it need to be always real? Why I am saying that? Because if you see, we are calculating it from the cos inverse of this. So what is the range of the cos x? The range of the cos x for real x is -1 to 1. We know that. Like x belongs to real number. Okay. So what can I say? if this thing, so I can say that 1 minus, sorry, 1 minus omega square m divided by 2k if the modulus is less than equal to 1, if that modulus is less than equal to 1, and if I just name it like lambda, then cos inverse of lambda will be a real number. Agreed? Any doubt? Any doubt? No doubt? Okay. So I can say that once 1 minus omega square m divided by 2k is less than equal to 1, my kappa will be real. Agreed? All of you? Okay? Agreed with that point? Nice. So now if you see this is, but you are inputting the omega and you did not put any restriction. So what is the range we can get it here? If I just quickly calculate it, I can see that, I mean, then here it will be minus 1. So I can, if I can just quickly write it, 2k no, I can just write it differently, just a minute, sorry. So if I just add plus, if I just subtract 1 from both the side, I will get it minus 2 minus omega square m by 2k should be less than equal to 0. Now what happened? I am multiplying with minus 1. If I am multiplying with minus 1, that means it will be like that. Agreed? So I can get it 4k less than equal to omega square m less than equal to 0. So one point is okay, that omega square is greater than equal to 0. So one limit is, I can say omega square is greater than equal to 0. Fine. And another limit I am getting, omega square should be less than equal to 4k by m. Now that is little bit point of caution. That tells me what? That if I am exciting it beyond certain frequencies, my wave number will become complex. They will be no longer real. All of you agreed with me or not? Please tell me. Agreed? Clear? Because you can very clearly see that thing. But up to this step, all of you with me? Anybody lost the track? No? Fine? Very good. So you can see that we will reach up to this stage, that omega square should be less than equal to 4k by m. Now, there is no literal sense that omega square is less than some value. Omega can be more than some value. But what is the consequence of that? If omega is more than some value, that means that time we will get our kappa non-real. It may be imaginary or it may be complex. Okay? Do you agree with me? Agreed? Very good. Now let's see if kappa becomes a complex number. What can we get? What does that mean? By the way, up to this stage is very clear. Na? Up to this stage is clear to all of you that it is restricting up to that certain value and perfect. Now let's go. So we have seen that. What was my equation? Okay. Now I can see that my kappa can be a complex number, because if I take it kappa as a complex number, it satisfied both the case. In some case I can say beta is equal to 0, and in some case beta is not equal to 0. That's all. Beta equal to 0 means it's a real value, and beta not equal to 0, that means it's a complex number. Simple. Okay, agreed? Very good. So now if you think, once I'm saying that this thing is alpha plus I beta, that means what? Now if I just substitute it here, I can get e to the power minus I omega t into e to the power of minus I alpha x into e to the power of minus I into I beta x. I can split it up from the index notation. Agreed? Agreed, all of you? Very good. Interesting thing. So once we have seen that kappa is real, that means what? My beta is equal to 0. Okay. Then my solution is what? Y of x comma t is equal to a into e to the power of minus I omega t into maybe alpha x. I'm just writing. Okay. Okay. Then just kappa equal to alpha. Fine. No doubt. But when k does not belong to real, then what? Then we can see that beta is not equal to 0, and we are getting x comma t equal to e to the power of I omega t into e to the power of minus I alpha x into e to the power of beta x. Now what is that term beta x? Now let's try to see and try to understand the full matter. Okay, so if I just think that this term is something which is varying with time. Agreed? This term is varying with, so this is varying with time, this is varying with space, varying with, actually a, you can say it is just amplitude scaling, so it can be space, it can be time, means it can be either of the sides, so it can go with t or it can go with x also. Okay, but if you just think like we are now primarily focusing on how we can able to look it into the space, so better consider a also with the time. Okay, and these two terms are in space, this is also in space. Okay, agreed? Now if you think how these terms look like, e to the power of minus I alpha x, how this term should look like? This is nothing but cos of alpha x minus I sine alpha x. Agreed? So what it is? It is basically a wave, or it's a sinusoidal motion. Okay, you may see that complex number here because that can give some phase difference. So that's why that complex number is coming here, but that hardly matter. So we are primarily getting what? We are getting a sinusoidally varying motion. Agreed, all of you? Okay. So that tells me that once the beta is equal to 0, we are getting a sinusoidal solution. Agreed? Now if, and then how this portion look like, e to the power of beta x, how it look like? So this is nothing but a sinusoidal. Okay. How e to the power beta x should look like? Sorry? Aperiodic. Okay. Any other better definition? Better answer? It is exponentials. If you think, if the beta is negative, then can you tell me what it is? It's a decay. If you think that your beta is less than 0, then it's a pure decay. No doubt on that. And if beta is positive, then it's a growth, exponential growing function. Beta equal beta greater than less than 0 is this, and beta greater than 0, you will get it exponential growth. Agreed? Agreed, all of you? Perfect. Now think, what is the significance it is telling? Once we are having, so now we understood that one portion, that this part is primarily a sinusoidally varying, very nicely periodic type of motion, and this part is demonstrating either a growth or a decay type scenario. It's basically a same function, like coming like this way. So if you are looking at, sorry, I little bit make a mistake, sorry. If you see that e to the power function exactly, it will go, it will not cross the line actually, will not cross the line. So if so, this is beta, so beta positive and beta negative, so beta negative. So once it is positive, it is growing, otherwise it is decaying. Okay. Now tell me one thing, once we are multiplying the two functions, what will happen? Agreed? So it is some sort of like a windowing effect. Once we are multiplying the two waveforms, we can thought it as like one is like a window and we are sending the other through that window. So it is getting small or getting R. So if you think that, so once your, so we have kappa equal to alpha plus I beta. Now if your beta is equal to 0, I will have a wave like this. Once the beta is non-zero, so first case we can think one case, that is So our function is alpha plus I beta. So you can think that one case beta is 0, another case beta is non-zero but alpha equal to 0. It can also be possible that alpha is 0. Solution is purely imaginary solution. Possible. In that case, what we can get? Exponentially decay. Our response will exponentially decay throughout that. Another case is beta is non-zero, alpha is also non-zero. In that case, what we will get? Decaying response. Okay, means it will decay, but it will decay in like oscillatory manner. In the first case, it is clear decay. Another case, it is decaying with oscillations. When the oscillations are decaying, once it is propagating. All of you agree with me? Now, if you try to recall the structural dynamics type thing, can you get some resemblance? Can you get some resemblance? Forced vibration, no, little bit. Think forced vibration, yeah, you can call it how? Damping, exactly. So if you think that this is something like undamped system, this is like underdamped system, and this is critically or overdamped. But what is the prime difference with the structural dynamics versus here? That is the axis. Here, what we are looking at on the space. But in dynamics, once we are plotting that, we are plotting that in terms of time. That's a big difference. Phenomena are very similar, but that's a phenomenal difference what definitely we should keep in mind. Okay. Do you guys understood? So this tells what? Like let's say we are sitting here in that room. There are several walls. After let's say 5 rooms later, can anybody hear our voice? Because you can think that walls are something like a mass, has some stiffness, air medium, again another wall, mass, some stiffness at the springs, again another wall. So how much wave is transmitting there? If we try to make a plot, can able to see that? Suppose metro is moving, we have a soil. That vibration is coming to the ground, yes or no? That is we can able to find out from here. What will be the profile throughout? We can able to find out from this. Get that point? What the spatial variation? In structural dynamics, we are only focusing on the temporal vibration. But here we try to see, in case of wave, temporal is also there. We also try to add how spatially it is distributing. It is not only the time we are focusing, we are also looking at how the spatially that thing is actually occurring. And then the combination of these two, we are giving a complete picture of that. Does that make sense? Point? Good.